All right, Chemistry 3101. This is our continuation with Chapter 6. And today we're going to spend most of our time looking at mechanisms and arrow pushing and variations on that. And so we've used curved arrows before in this class. We started with curved arrows when we were talking about resonance structures, and we spent a lot of time on resonance structures. And so you should have an idea already about the fact that curved arrows are nothing more than a representation of the flow of electrons. Again, we use them in acid-base reactions, and we use them in resonance structures. You should know that when you see a curved arrow, a couple of things right off the bat. When you have a double-headed arrow like these ones here, it shows the flow of two electrons, right? This first arrow represents the movement of two electrons, and this one represents the movement of two electrons. How do they differ? Well, this curved arrow here represents a bond being formed, right? The bond between the base and the proton. And then this curved arrow here represents a bond being broken. Okay, so here you see that we have a bond being broken and a bond being formed simultaneously. So two arrows at the same time. All right, there's four main ways that electrons move in polar or ionic reactions, which is what we're going to be concerned with most of the time in this class. Those four are nucleophilic attack, which we use Na to represent. Then we have a loss of leaving group, LLG, a proton transfer, or a PT, and a rearrangement, RGT. So we're going to look at all four of these ways that electrons can move in greater detail. So a nucleophilic attack. During the last lecture, I discussed what a nucleophile was and what an electrophile was. So a nucleophilic attack is when a nucleophile is going to attack an electrophile. How do we know this is a nucleophile? Well, it's got a negative charge. So it's going to be seeking a nucleus. Nuclei are positive, right? So a nucleus or an electrophile is going to balance that charge out. We have our electrophile over here. We discussed during the last lecture why a carbocation is a good electrophile. It's electron deficient, so it's ready to accept electrons from the nucleophile. And again, you see that this curved arrow here, the tail starts on a pair of electrons. The head ends exactly where the electrons are going, which is to this carbon right here. And this curved arrow shows a bond being formed, right? And that bond that's being formed is this new sigma bond right there. So again, it's important that you are accurate or precise in drawing the tails and the heads of arrows. So the tail is always going to start on a pair of electrons or a negative charge oftentimes, and the head is going to end on a nucleus or a positive charge. Okay, the electrons end up being shared because we are forming covalent bonds. Okay, we're not forming ionic bonds, not a whole heck of a lot in organic chemistry. All right, nucleophilic attack sometimes can require more than one curved arrow. Here you see the nucleophile. You see this alcohol is behaving as a nucleophile. It doesn't have a negative charge, but during the last lecture we said, well, if you have a pair of electrons, that can behave as a nucleophile, again, depending on the situation. Why is this acid chloride, why is this carbon an electrophile? The reason why is because there is a strong dipole between the carbon and the oxygen. There's also another one here, and so this carbon is partially positive. So the partial negative charge on the lone pair of the nucleophile is going to be attracted to that carbon, which is our electrophile. We could call it an electrophilic center. Now, the problem with just drawing one arrow here, the reason we have to have two arrows drawn on this slide is if you were to do this, and don't do this, but if you were to draw out your alcohol, draw the acid chloride, okay? And if you were to just draw one of those curved arrows like that, the problem, and it's a major problem with that, is that you would end up with something that looks like this. You'd have the carbon with the double bond to oxygen, you still have your chlorine, you still have this methyl group, right, this CH3 group, but then you've got a bond to an oxygen like this, okay, and it's going to have a positive charge. This carbon has exceeded an octet, okay, which is impossible. That carbon has 5 bonds. Sometimes we call this the Texas carbon. There's no such thing as a carbon that can exceed an octet. Remember, the elements in the first and second period cannot exceed an octet of electrons. And so that is why when you draw this curved arrow, you have to simultaneously draw this one here, which shows the movement of the pi electrons up to the oxygen, like that. All right, there we go. So nucleophilic attack, again, can require more than one curved arrow. There's no such thing as a carbon with 5 bonds. So if you're ever drawing curved arrows, practicing at home, and you end up with a carbon with 5 bonds, you've got a serious problem, okay? And you have to fix that problem. Pi bonds can also act as nucleophiles. This is something that we're going to see more later on. So this will be more of an organic chemistry 2 thing. But here you see that you have a molecule of sulfur trioxide. This is SO3. This is just the Lewis structure of it here. But you see that benzene is behaving as a nucleophile, and the sulfur in the sulfur trioxide is behaving as an electrophile. And we have a nucleophilic attack by an aromatic ring, which is kind of interesting, okay? But the bottom line for us right now is that pi bonds can also act as a nucleophile. And that was also in the table that we looked at last class. We said, okay, a pi bond can be a nucleophile. Also, just one little point here. When you're, calculating formal charges in the result, of the intermediate that's produced after a nucleophilic attack, for example, here you see you have a positive charge, here you have a negative charge. Okay, fine. Well, there's only a positive charge on one of the carbons of the double bond, right? It only ended up on this carbon here, which tells us that the pair of electrons, okay, since the bond is formed to this carbon here, that this carbon has one hydrogen attached to it, and it only has one hydrogen over here, right? That didn't change. So since this carbon only has 3 bonds, it's going to have a positive charge, right? These are just kind of bookkeeping things that you want to keep in mind while you're moving along, right? This carbon also has a hydrogen, but it's here too. And so only one of the carbon atoms in that pi bond actually get the benefit of the pair of those electrons, and the other one is going to be electron deficient and renders it a carbocation in this case. This reaction is something that we call electrophilic aromatic substitution, which is, again, covered in chapter 18. It's a big part of organic chemistry 2, and you'll learn all about it when you take that class. All right, nucleophilic attack. Well, what about the loss of a leaving group? And if you're wondering, what's a leaving group, Mr. Dion, we're going to qualify what that is. Loss of a leaving group, again, we use LLG. I'll use the shorthand. If we go back here for nucleophilic attack, I'll usually use Na instead of writing out all that. But a loss of a leaving group is a heterolytic bond cleavage. Remember, a heterolytic bond cleavage is when one atom takes both of the electrons. The other one is left with none of the electrons from the bond, okay? Here we have this molecule. This is tert-butyl chloride, and you see we have one curved arrow here. Well, if you look at that curved arrow, you see that both of the electrons in this bond are going to end up on the bromine. So bromine has 1, 2, 3, 4, 5, 6 unpaired electrons, and now it's going to have 8, which renders it a bromide. Okay, you need to know how to calculate formal charge quickly. And then you see that this carbon here goes from having 4 bonds to having only 3, which renders it a carbocation. So we have a leaving group that's lost. Now that is a one arrow representation, or one curved arrow representation of a loss of a leaving group. But loss of a leaving group can have more than one curved arrow. Here's an example, okay? It says here that you can have more than one curved arrow to show the loss of a leaving group. And if you're wondering, whoa, this looks pretty crazy, Mr. Dion, you got 4 curved arrows. I'm not sure what that is, okay? But that's a nitro group on the end here. And what's happening is the chlorine is being lost as a chloride here. Okay, the chlorine is being lost as a chloride, but we have to draw all 4 of these curved arrows in order to show the chlorine being lost as the chloride. If you look at our textbook, at this section, the loss of the leaving group, he shows you another way to do it, where you just draw this arrow first, and then you draw basically a resonance arrows after. But this will be the preferred method in this class. And if you're wondering, what would you get after that? Well, we could draw that out, right? We could just draw what we'd have. You see that we have our bond to our nitrogen. We have 2 oxygens here. The oxygen on the top left is not being changed at all. I'm forming a double bond here, like that. This pi bond is being broken. So now I'm going to have a pi bond here. I'm going to have a pi bond here. This one remains untouched. And now I have my hydroxyl here. I have a positive charge on my nitrogen because it's got 4 bonds and no lone pairs. And I have my chloride being lost. Okay, so you got to be able to be accurate at keeping track of the electrons, but this is a loss of a leaving group. Okay, and again, we're going to talk more about what leaving groups are, or what a good leaving group is. Proton transfer, this is kind of acid base here. A proton transfer requires two curved arrows. So if we have hydronium in solution, so this is just H3O plus, it's just the Lewis structure of it right here, okay? If we have hydronium, we know that hydronium is a strong acid. It's got a pK of around minus 1.7 or minus 2 is fine. And what's happening here is the oxygen at this carbonyl is donating this pair of electrons, and it's taking a proton from the hydronium. So it's becoming protonated, and then of course we'd be left over with water in this case. But you see that this is a 2-arrow process. Now this will be our preferred method for drawing proton transfers, will be to use 2 curved arrows in our proton transfers. The deprotonation, again, I like my students to draw as 2 curved arrows because it's the easiest way to keep track of the electrons. So you see that this protonated carbonyl here is losing this proton to the water, which is behaving as a base. So what's going on? The pair of electrons on the oxygen is taking the proton, right, or forming a bond between the oxygen and this proton here. And then this bond is being broken, and the pair of electrons is going to end up on the oxygen of the carbonyl. If you're the kind of person who likes to peruse the internet and look at all kinds of, other videos or sources on organic chemistry, you might see this from time to time. What's here at the bottom right-hand side of the screen, I would recommend not doing that. Okay, that's a single arrow. That is used by chemists sometimes to kind of keep reaction mechanisms a little bit cleaner, to avoid having too many arrows. But trust me, you do not need to do that in this class. I highly recommend being, drawing a complete set of arrows. Don't try to draw any shorthand. Once you master the subject, then you can try drawing shorthand, but I wouldn't recommend it now. Also, multiple arrows are going to be necessary sometimes when we show the flow of electrons. So here we have this ketone, so this is acetone, which is just nail polish remover. You have a hydroxide, which is a strong base. It's removing this proton. I want to point out that this molecule that's drawn right here, this is acetone, okay? It's this molecule right here. We have a methyl group here, and we have a methyl group here. They're just isolating one of the hydrogens on purpose. So what they're drawing is this, CH3, and then you have the carbonyl. Then they're saying CH2, and they're showing one of the hydrogens kind of off to the side just for mechanistic purposes. And I'll do that from time to time. So it doesn't mean there's only one hydrogen attached to that carbon. That's impossible, right? You know that there are 2 other hydrogens. They're just not drawn for simplicity's sake, to make it actually look a lot cleaner. So what's happening here is the hydroxide is abstracting, which means simply removing this proton to form water. And then you see that this pair of electrons, maybe I'll highlight it in yellow, this pair of electrons is going to form a pi bond here, but that would render this carbon with 5 bonds. And so the pi bond is being broken. And then we're going to end up with a pair of electrons, an extra pair of electrons on the oxygen. Now you might think that's a lot of curved arrows, Mr. Dion. Is there a simpler way to do it? Well, you could consider this proton transfer to be thought of as a proton transfer combined with a resonance. Now, if you're wondering, what the heck does that mean? Well, if you were to remove this proton, okay, it's just a proton transfer, right? Take this pair of electrons and put it on the carbon. Then you have a carbanion, and then you can just draw a resonance structure. In either case, this is fine. Now, if you're like, oh no, how am I going to know when to do what, and when to do what, when, again, this is one of those content areas where practice is going to help the concepts crystallize in your mind, and it will alleviate any fears that you have, okay? Trust me, many people have studied this before you. Many people will do it after, okay? So it's something that I promise that if you practice it, you will figure it out, okay? Or it will become clearer, I should say. And then the last one is a rearrangement, for which we use the abbreviation RGT. And there are many types of rearrangements that can occur in organic chemistry, but there's only 2 types. One type would be the carbocation, and there's 2 types of carbocation rearrangements that we look at in Chemistry 3101. Now, if we go back to carbocations, let's talk about them for a second. right? You know that a carbocation occurs when we have an sp2 hybridized carbon that is missing a bond. It doesn't have a bond, so it's going to have an empty p orbital that has a positive charge, right? You can all recognize a carbocation by now. The point is this: when you have a carbocation, if you have neighboring groups, neighboring alkyl groups, like a methyl or an ethyl or a propyl or a butyl or a decyl or whatever, okay, as long as you have some kind of alkyl group, it actually serves to stabilize the carbocation through a process that's called hyperconjugation. Now that's kind of a long word, but it's going to come up quite a bit in organic chemistry. It comes up in this organic chemistry. It's going to come up in organic chemistry too. Okay. Now I'm not going to ask you a whole lot of questions like, oh, draw this for me and show me how, some of the orbital electron density here is going to flow into the empty p orbital and stabilize it. I'm not really going to ask you about that. What I want you to know is what's on here. Is that if we go from a methyl carbocation to a primary where we only have one R group, to a secondary where we have two R groups, and to a tertiary where we have three, the more R groups that we have, the more stable the carbocation becomes. It says increasing the substitution increases the stability of a carbocation due to the increasing number of adjacent sigma bonds. And the sigma bonds donate electron density to the empty p orbital via the process of hyperconjugation. Okay, so again, if I only had 5 seconds to teach you this slide, we had to leave immediately, I would just say the more R groups you've got on a carbocation, the more stable it becomes. And this is a rule that you're going to see invoked time and time and time again in organic chemistry, such that students usually master this pretty quickly. Okay, it comes up a lot in organic chemistry, and it even comes up sometimes when it kind of surprises us. You'll be in the middle of learning something in organic chemistry too, and you'll say, hey, look, there's going to be a carbocation rearrangement. But we're going to look at some examples right now. So the two types of carbocation rearrangements that you have to be concerned with are called a 1,2 hydride shift and a 1,2 methyl shift. Now a hydride, you should remember that if you have hydrogen on the periodic table, right? You look at the periodic table, hopefully you have one in front of you, and you look up element number 1, it's hydrogen. But you know that when hydrogen is found in a pure sample, it exists as hydrogen H2, right? This first one is hydrogen, an atom, just an atom of hydrogen. The next one is a molecule of hydrogen. You also should know that H plus is what we call a hydrogen ion, or we usually call it a proton, right? Because a hydrogen atom consists of only one electron and one proton. If you remove the electron to make a positive charge, what are you left over with? You're left over with the proton that's in the nucleus, and so we call this a proton, okay? Then there's one more type of hydrogen you need to be concerned with, and that's a hydrogen with an extra electron, which has a negative charge, and that is called a hydride. Now, if you're like, I've never seen that before, you should have seen it in General Chemistry 1 when you looked at naming ionic compounds like NaH, which would be called sodium hydride, okay? The sodium has a +1 charge, and the hydrogen, in this case, has a -1 charge. So again, the reason you need to know what a hydride is because a hydride can do this rearrangement called a 1,2 hydride shift. Sometimes I'll just call it a hydride shift, okay? Now look at what's happening here. If we look at the carbocation in this molecule here, this is a secondary carbocation. And so you have to look at the two carbons that neighbor it, right? Here's our secondary carbocation. We look at the two next door neighbors. I'll highlight them both in green, okay? Well, maybe I'll use two different colors. I'll use red for this one here. The one that's highlighted in green, if you move this hydrogen over, right? If you take the hydrogen with the pair of electrons in this bond, so if you shift the hydride over, you end up with a tertiary carbocation, which is more stable on account of hyperconjugation. Now, there's not a lot of room here, but I'll just show you quickly if you're wondering, well, Mr. Dion, why can't I take one of the hydrogens here? The reason why, and I'm just going to quickly scribble this in here, if you were to draw this as your curved arrow, then you would end up with this, and you'd have a primary carbocation, which is very, very unstable. And so that's not going to happen. The only time rearrangements are going to occur is when you make something that's more stable. So here, since we're going from a secondary to a tertiary, we're getting something that's more stable, so it's going to happen. Look deep into my eyes and I'll hypnotize you, okay? The bottom line with rearrangements is this: if they can occur, they will occur. Give me a thumbs up if you follow me just on the hydride shift. If you're like, yeah, hydride shift, I think I got that. And we'll look at some examples of it. Does everybody follow me on that hydride shift? Okay, good. Okay, great. And again, we'll look at some examples of it. We just have to get through some content before we start doing some practice. The next one is a 1,2 methyl shift. If you are the kind of person, again, who likes to Google everything, the textbook that I grew up with called this a methide shift, because technically you're moving CH3 with a lone pair, which would be called a methide. Sometimes if you research this on the internet, I think the proper name is a methanide shift, okay, is what it's called sometimes. Again, your textbook that you paid for is only ever going to use this term, okay? So don't stress about, oh, I know some other terms that aren't in my book. No. The same thing is occurring here. We're going from a secondary carbocation. We have a methyl group here. It can do that methyl shift, moves over here, and we produce a tertiary carbocation. Notice that when we're examining the initial carbocation, we can only look at the neighbors. If you have a big molecule, okay, let's say you had something like this, and here's the point right here. Shifts can only occur from an adjacent carbon. Let's say you had a big molecule like this, okay, and you had a secondary carbocation right here, and you have a methyl group over here. You cannot be like, oh, just grab that. No, you can't do things like that. You could only look at the next door neighbors, meaning you could only look here and here. If you were to do a hydride shift from either of these carbons that I have highlighted in yellow, all you'll end up with is another secondary carbocation, so it's not going to occur. It only happens if you end up with a more stable carbocation. It doesn't just happen for fun, okay? It happens when you end up with something more stable. All right, so what you're going to see is these 4 patterns of arrow pushing: the nucleophilic attack, loss of leaving group, proton transfer, rearrangement. You're going to see them put all together to tell the story of the mechanism of a reaction in organic chemistry. When we look at multi-step reaction mechanisms, and we're going to look at a hell of a lot of them. In fact, if you read the textbook before coming to class, which I implore you to do, he mentions the fact that in this class there's probably over 100 different mechanisms that we'll look at throughout the course of Organic Chemistry 1 and Organic Chemistry 2. But he said every single one of the steps in all of these mechanisms that you're going to see are going to be some combination of the 4 patterns that you've seen thus far. Check out this reaction right here, and this is our starting material, and we're ending up with this product, okay? Here's our reagent. So what's happening is you're taking this alcohol, you're treating it with hydrogen bromide, and you end up with this alkyl bromide over here. But what is being shown here are all of the steps of the that show the actual reaction mechanism, the actual flow of electrons. You see that the first step, we have the hydroxyl from the alcohol, and what's happening is it's accepting a proton or taking a proton from the HBr to become a protonated hydroxyl, okay? And then we have a curved arrow that shows water leaving, right? Notice that you're losing what? You're losing H2O. You see the 2 hydrogens and the oxygen, you're like, well, this water's got a positive charge. No, it doesn't. Not at the end of the loss of leaving group. Look, you have this pair of electrons that's going onto the oxygen, so you're going to lose H2O, and that's what that negative H2O means. It means water was lost. Now this carbon right here, okay, which has a hydrogen attached to it as well, which isn't shown, but now that carbon is deficient, okay, it's electron deficient, and now you've got a carbocation. This is a secondary carbocation. It's going to undergo a 1,2 methyl shift in this case, and look what you end up with. You end up with a tertiary carbocation. Then your nucleophile is going to come in, and it's going to attack the carbocation. That's what we call a nucleophilic attack. Right? Opposites attract, and you end up with a tertiary alkyl halide in this case. So we saw all four of those mechanisms that we've learned: the proton transfer, the loss of leaving group, the rearrangement, and the nucleophilic attack all occurred in this one reaction where we converted the secondary alcohol to a tertiary alkyl halide. Something also that you're going to see is that oftentimes two of these four mechanistic steps that you've learned, the proton transfer, the loss of leaving group, the carbocation rearrangement, the nucleophilic attack, oftentimes two of them are going to happen at the exact same time. Look at what's happening here. We have the hydroxide behaving as a nucleophile. So this part right here, this is a nucleophilic attack, right? This is my nucleophile. This carbon is my electrophile, right? Because there's a dipole going this way. The carbon is partially positive. I'm going to erase some of this spinach to clear it up a little bit. But anyhow, we have our electrophile, we have our nucleophile, and then you see that we have a loss of leaving group, right? The chloride is being lost simultaneously. We call these concerted reaction mechanisms, two steps occurring at once. All right, with all that in mind, let's take a look at an example. Now, this is, again, one that comes straight out of our textbook, okay? And we've got three steps. We have step number 1, okay? We have step number 2, and we have step number 3. So if we just look at the first step, okay, we just isolate what the heck is going on here. Could anybody tell me, is this a proton transfer, a nucleophilic attack, a loss of leaving group, or a rearrangement? It's got to be one of those four. But could anybody identify what's going on in the first step? What does it look like? Yeah. So we don't want to get confused. Hydroxide can behave as a nucleophile, right? We see hydroxide behaving as a nucleophile right here, okay, when it's being attracted to a nucleus. But we know that hydroxide is also a strong base, right? So depending on the situation, hydroxide might be behaving as a nucleophile, which would still render it a Lewis base. But anyhow, here what's happening is the hydroxide is taking this proton, right? So this is a proton transfer step right here. This is a proton transfer, right? There's something that's being left out here. When you form this carbanion right here, right? This pair of electrons, okay? Let me erase some of this. This pair of electrons from the sigma bond is ending up right here on this carbon to form a carbanion. But something that it's not showing is that you also formed water, right? It's just left out because it doesn't serve any purpose, right? When you combine the hydroxyl with the proton, you form water. It's just not included, okay? So there's a proton transfer in our first step. If we move on to step number 2, so here's the second step. We have this carbanion right here, okay, and then we have 2 arrows. Could anybody tell me what's happening in this step? What does it look like? Yeah, this one's a nucleophilic attack, right? My carbanion is acting as a nucleophile. This carbon is my electrophile. It's partially positive, okay? So the nucleophile is attacking the electrophile. And as I showed you earlier today, you can't form 5 bonds to carbon. And so this pair of electrons is going up onto the oxygen like that. Okay, there we go. That's the second step. And then here's the last step right here. I'll give you a second to think about it. What's happening in this step? Yeah, I think this one might be more abundantly clear that this is the loss of a leaving group, right? This one was a nucleophilic attack. Anyhow, so this one is a loss of a leaving group, right? It required 2 curved arrows to show that this pair of electrons is going to form a pi bond right here, which is this new pi bond. And this bond, maybe I'll highlight it in yellow, this bond is being broken, and you're going to end up with, there's already, two pairs of electrons on the oxygen, and you end up with a third pair, and so you end up losing this alkoxide. So this is a loss of a leaving group. Okay, give me a thumbs up if you follow me half of the way there. We'll look at some more. We're going to do some more practice. I just want to show you some more rules that deal with curved arrows. You don't want to break the rules when you're drawing curved arrows. And if you think back to a lot of the concepts that you've learned thus far in the class, you'll think about a lot of them and remember how you felt when you were first introduced to them. And I've taught organic chemistry for a long time. I know that students can sometimes get intimidated, but hopefully you've figured out that in organic chemistry, that once you start to practice it, it starts to become a lot clearer. Okay? All right. Next, it says drawing curved arrows. So this is a little David Klein sort of rabbit path that he kind of goes off on, which is really handy, actually, section 6.10. He just kind of shows you some things to do and not do, okay, with respect to curved arrows, some traps that students might fall into. And just to give you some advice on drawing curved arrows, first point, it says curved arrow, it's going to start on a pair of electrons. I've told you that probably 3 or 4 times already. The tail of the arrow always has to start either on a bond or a lone pair, one or the other, okay? Always has to start there. You see this first curved arrow for this right? This is a nucleophilic attack that's occurring here. Starts on the pair of electrons on the alkoxide. And then we have a loss of leaving group occurring with the second curved arrow. But you see that the tail of the arrow starts on a bond, okay? Don't start bonds or don't start curved arrows. A curved arrow could never start on a nucleus like that, okay? So the second arrow is drawn incorrectly in this mechanism that's drawn here. The first arrow is fine, right? We know that we have 3 lone pairs. That's okay. But the reason this doesn't show a loss of leaving group is because the arrow has to start on a pair of electrons. It should look like that, okay? The arrow that's drawn in black is incorrect. Never place the tail of a curved arrow on a positive charge, okay? If you do that, you know you've got a problem right away. What's another handy dandy point here? It says the arrow's got to end on a nucleus, okay? If it becomes a lone pair, or between 2 nuclei if you're forming a new bond. So we see that we're forming a bond between this oxygen and this carbon, right? That's this bond right here in the bond forming step, in the nucleophilic attack step. And then you see that the second curved arrow ends up on the nucleus, on the carbon, so that we end up with a chloride. More importantly, I would say never break the octet rule, right? You guys remember the octet rule from general chemistry? If you think about it, there's actually very few elements on the periodic table that strictly abide by the octet rule. Only a few, only a handful, okay? Like nitrogen, carbon, oxygen, fluorine, right? Outside of that, we have all kinds of exceptions to the octet rule, and I know that elements can exceed an octet from the 3rd period and beyond because they have the d orbitals available to them, but that's neither here nor there in our class. You're never going to have a carbon with 5 bonds. You're never going to have, a nitrogen that exceeds an octet, or an oxygen, or a fluorine that exceeds an octet. It's just not going to happen. In fact, I told you way back in chapter 1, I wouldn't expect you to remember every little nuance that I said in chapter 1, but I told you that we're never going to look at, exceptions to the octet rule, not in chemistry 3101. There we go. Let's see. If you draw an arrow, it's got to represent one of the 4 patterns that we've looked at, right? If you draw something like this, that is just crazy. I don't even know what's going on there, okay? And sometimes I'll see students draw wacky arrows, but you see how you're starting on a pair of electrons. That's cool, but you're ending up way over here, okay? It's totally unreasonable. You're violating the octet rule, right? Because this is a CH2, you'd have 5 bonds. I mean, it's just, I don't know what the hell is going on there. So that's just way off in left field. All right, well, let's take a look at a question. Now, this is the type of question that I would ask if we weren't in the middle of a global pandemic and we were doing paper quizzes. I would give you something like this, and I'd say, take your pencil and draw the curved arrows that accomplish the following. A nice place to start, and I know that a lot of my students like to start here, is just by drawing in all the lone pairs, right? This goes all the way back to chapter 1 when you're practicing drawing lone pairs. How can they come out like that? Anyhow, there we go. So now we have all the lone pairs drawn in like that. Could anybody tell me what's happening in this mechanism? I know that you can't draw it for me, but is this a nucleophilic attack, proton transfer, loss of leaving group, or rearrangement? Can anybody tell me what's happening here? Yeah, thanks, Kayla. It's a nucleophilic attack, right? The water is behaving as a nucleophile. So this is my nucleophile. This is my electrophile. And I'm going to have a curved arrow drawn from, maybe I'll use red, okay? From a pair of electrons. I start on a pair of electrons, and then my curved arrow is going to head towards the nucleus, like that, okay? And that's it. That's my curved arrow. That's the only thing you'd have to draw in here. Now, if you're wondering, can my curved arrow, I drew my curved arrow over here, Mr. Dion. There's always somebody who wants to split hairs, you know? That is fine, okay? If you want to draw the arrow like this, that's fine, to the positive charge. Technically, if you do this, okay, if you were to do this, okay, technically it's correct, okay? I wouldn't do that. I would grade that you're insane or something. You need to see somebody. But technically it's correct. It's a curved arrow that shows a flow of 2 electrons to a nucleus, okay? So it doesn't matter if you draw your arrow exactly like me. Once you get used to drawing mechanisms, you try to draw them as cleanly and as neatly as possible. And since I'm left-handed, I always try to, sometimes I'll take the long way around just so it looks cleaner to me. Anyhow, there we go. So that's the kind of thing you got to be able to do, but you have to be able to do it over and over and over and over again, right, in this class. What else? When you encounter a carbocation, you got to consider whether it's going to rearrange or not. Okay, so anytime you see a carbocation, you should ask yourself, is this thing going to rearrange in some way to give me something that's more stable? You start by looking at the carbon with the positive charge. You look at both of the next door neighbors. This is a next door neighbor. This is a next door neighbor. If you were to circle any of this, that's not next door neighbors. Next door means immediately next to. Okay? So what's attached to the green carbon? It's got 2 hydrogens attached to it. And on the blue carbon, the only thing it's missing there is a hydrogen, like that. Could anybody tell me, would a rearrangement occur here? Yes or no? Yeah, the answer is yes. A carbocation rearrangement will occur. So this here is a secondary carbocation. If you were to move the green hydrogen over like that to do a hydride shift, let me show you what you'd end up with. You would end up with this. You'd have this, okay? And then the positive charge would migrate from here to here, right? Well, that's not a curved arrow, but you'd end up with the positive charge here because now you'd have, it's already got a proton attached to it, which is here, but now you would have moved the green proton and you'd only have 1 proton here. But this is also a secondary carbocation, so this is not going to occur. Maybe we could do better than that. There we go. Not gonna do it, right? It's George Bush Sr., right? Anyhow, so what's going to happen is somebody said the blue proton is going to move. So I'm going to erase this spinach here and clean it up. And the blue proton is going to shift over here, okay, and fill that p orbital up. And look what we're going to end up with is this molecule. We'll have these 2 carbons like this. And now our positive charge is going to be here, right? Because we've got no proton attached to that carbon with the positive charge. And now the adjacent carbon has the black proton, and it also has the blue proton that moved over in the hydride shift. Okay, so this is a 1,2 hydride shift. And yes, it's going to occur because we go from a secondary carbocation to a tertiary carbocation. So yes, sir, that's going to happen. Give me a thumbs up if you follow me on that one. Cha or no? Okay, good. All right, because the next slide basically covers everything that I just drew out. Okay, it's just shown on a slide. I like to kind of go over that with my students. So this is just a summary. If you were to shift one of these protons, you end up with a secondary carbocation. However, if you shift this proton, right? You end up with a tertiary carbocation, which is more stable. So always ask yourself, is it more stable? Yeah. There's one more nuance to the carbocation rearrangements. If you look at this carbocation that's shown on here on the left, this is a tertiary carbocation. It's a beautiful carbocation, stable. And you might say, it might be a knee-jerk reaction to say, well, a tertiary carbocation is as stable as you're going to get. It's never going to rearrange, not going to happen, okay? That's untrue. A carbocation can rearrange if you form a tertiary allylic carbocation. So if you make something that's more stable. So we go from a tertiary to a tertiary allylic. Remember, right? These positions here are allylic positions, right? These ones here are what we call vinylic positions. So this would be allylic carbocation because it's next to the carbon on the double bond like that. And what makes it so damn special is that it's resonance stabilized, okay? So you end up with a carbocation that's even more stable because it's stabilized by resonance. So again, just because you have a tertiary carbocation doesn't mean like, oh, that's the end of the road, nothing's ever going to happen to this. If you can have a hydride shift, and that's what's happening here, is you have a hydride shift, okay? If it can happen to produce something that's resonance stabilized like a tertiary allylic, it will happen, okay? All right, so you see how an organic chemist has to really be on her or his toes, you know? When you're reading literature or you're working in a lab doing research, you've got to be, you know, a quick thinker. You got to be able to assess everything at all times. You're always doing what we call the 30,000-foot view. You know, when you're an organic chemist, it's really hard to just zoom in on one thing and look at that. You've got to look at everything at the same time when you're an organic chemist. It's a big part of the skills that it takes to master organic chemistry. All right, last section of section 6.12 is one of my favorite sections of this entire textbook. It's something that we go over today, and like I said, it's going to come up a lot. I usually don't beat my students up about this section a whole heck of a lot. I mean, I might ask you a question or two about it on this quiz, but you're going to see in mechanisms that we look at throughout Organic Chemistry 1 and Organic Chemistry 2, sometimes in our step, like for example, in this first step here, this is a proton transfer, okay? The alkoxide is taking the proton. And then in the second step, this is a nucleophilic attack. But you notice that the arrows, the first ones are reversible, the second one's an irreversible. And students sometimes get really confused about when do I draw an irreversible arrow, when do I draw a reversible, how do I know? And the question is answered both by kinetics and thermodynamics. There's some really quick and dirty rules that are put forth here by David Klein in our textbook that enable you to decide whether you're going to write down an irreversible or a reversible arrow during a mechanistic step. So we'll start with a nucleophilic attack. Okay, so we're starting with the good old Na. Okay, if the nucleophile is also a good leaving group, it says that it's going to be a reversible attack. Now, if you're wondering what a good leaving group is, a good leaving group is going to be the conjugate base of a strong acid. Right? Because remember, the conjugate bases of strong acids are going to be weak bases. They're going to be stable, right? They're going to be stabilized. And so since water, H2O, is a good leaving group, this is a reversible nucleophilic attack, right? The nucleophile is water. Water is the conjugate base of a strong acid. You're like, what's that strong acid? Well, you should know it's hydronium, which has a pKa of around negative 1.7. Okay, so that's going to be a good leaving group. So again, conjugate base of a strong acid. What are the other strong acids? HBr, HI, HCl, things like that. Okay, so the reverse process is going to occur at an appreciable rate. Here we have the nucleophilic attack, and then here this would be the loss of the leaving group, right? But again, they can both occur at an appreciable rate. So that's nucleophilic attack. It says here that if the nucleophile is a poor leaving group, it's going to be irreversible. Now, why would this methide, this CH3 minus, this methyl carbanion, why would that be a bad leaving group? Because CH3 with a minus charge, which I just called a methide, or you can call it a methyl carbanion, either way means the same thing. But this is the conjugate base. Come on. Conjugate base of a weak acid. Okay, it's the conjugate base of a super weak acid. Methane is the conjugate acid of CH3 minus. Okay, methane is a pKa of around 50. So that's about as weak an acid as you're going to get. And so that is why it is unstable, right? It's not stabilized. Once it gets into this situation, it's going to be happy as a clam. It doesn't want to leave. And so this process, you're not going to lose a methide or a methyl carbanion. Okay? So again, you always got to be on your toes with things like pKa, strong acids, weak acids, right? These are the kind of things that you've always got to be evaluating when you're an organic chemist. Loss of leaving group, here's a quick and dirty rule for you. Loss of leaving group, the LLG is basically always going to be, it's just virtually always reversible. So even if you just guess, you're going to know if you got it right or not. I just told you the answer for this one here, okay? I told you how to identify good and bad leaving groups. And what I just told you, that the good leaving group is the conjugate base of a strong acid. A bad leaving group is the conjugate base of a weak acid. That's going to get you through everything you need to know in Chapter 6, okay? Trust me, you don't have to learn Chapter 7 to master Chapter 6. Not the way the book works, all right? It says it right here. Weak base, good leaving group, strong base, poor leaving group. Simple as that, all right? There we go. And then the last one is the proton transfer. What the heck? You know, we're going to see probably more proton transfers than any of the other 3 mechanistic steps. Sometimes in a proton transfer, the arrow is drawn as irreversible. Sometimes it's drawn as reversible. Here's the rule. And again, if you've read the textbook, you saw that he said, well, there's so many things in organic chemistry that you have to kind of take with a grain of salt. Right? If you go back to some of the rules that we've already learned, we said, well, you know, there's exceptions to most of these rules. But anyhow, here's a rule that's going to work for you 99% of the time in Chemistry 3101. And that is, if the pKa difference is 10 units or more in a proton transfer, it's irreversible. If it's less than that, it's reversible. Right? So here, if you have, oops, where's my pen? If you have the base, right, and your water is behaving as an acid, here you have the conjugate acid, and here you have the conjugate base. You evaluate the relative pKa's of the 2 acids, the acid and the conjugate acid. You see the difference here is what, more than 36 log units. So that's 10 to the power of 36, and so we have an irreversible arrow. If you do the same exercise here, here's your base. Water is behaving as an acid. This is your conjugate acid. This is your conjugate base, right? These are skills that we learned way back in the acids base chapter. You evaluate the relative pKa's of the acid and the conjugate acid. It's only 2.3 log units. It's less than 10. Therefore, you draw an irreversible arrow, and that's it, okay? The reason I said this is one of my favorite sections is I find students tend to, it's not my favorite because students forget it, but it's just one of those things that students tend to forget this section for some reason. When we move forward, we're just get so focused on mechanisms that students will sometimes bring this up to me in organic chemistry too. They'll be like, well, how do you know when the arrow's reversible or irreversible, Mr. Dion? And I'll always answer, it's probably the only chapter and section that I have memorized in the entire book. I'll say, go back to section 6.12 and look at it really quickly, and you'll see the rules, all right? And then the last one is a pretty easy one. Carbocation rearrangements are going to be irreversible, okay? There's nothing that's going to, there's no thermodynamic force that would, you know, go, cause the reaction to go in the opposite direction. I mean, what the heck would that be for, okay? Nothing. If you end up with something that's going to be more stable, right? Well, it's not going to go in the reverse order, okay? Also, there's some good ones. There's some beauty ones here, like this one here. If you look at this reaction that's happening here, you see that you're losing N2, right? And you guys know that nitrogen is a gas. So think about it. If you had this step occurring, this is a loss of a leaving group, okay? But nitrogen is your leaving group. Well, nitrogen is a gas. So if you did this reaction in a fume hood in the lab, you would see bubbles being formed, okay? These bubbles are going to go up into the atmosphere. They're not coming back, okay? So if you ever have a gas involved in a reaction like this, of course it's irreversible. The gas is, entropy is increasing, so you're not going to, it's increasing greatly. The gas isn't going to come back, okay? Not going to happen at all, okay? And that covers all the content in chapter 6. Let's take a look at some arrows. So I had some problems here. Oops, that's not it. Where are they? Chapter 6, practice problems. But before we do that, I want to ask you a couple of questions that deal with carbocation rearrangements. Okay, then we're going to get into some more arrow pushing. I'm going to draw some carbocations here. Okay, let's start with this one. And this one. And draw this one. No, let me take that double bond out. I want to ask you, we'll call these A, B, and C. I want to ask you about A. Would a carbocation rearrangement happen in A? Just a quick yes or no. Does anybody else have an answer? Okay, good. All right. Seems like a lot of my students are saying yes, a carbocation rearrangement would occur. Right, here's my carbocation. Okay, I look at the two next door neighbors. I look over here and I look over here. If I was to shift one of the hydrogens from the blue carbon, I would still end up with a secondary carbocation, wouldn't I? Okay. However, if I shift one of these methyl groups over here, if I do a 1,2 methyl shift, what do I end up with? Let's draw. We'd end up with this, where we have the methyl group over here. And now instead of this carbon having 4 bonds, it's only got 3. And so it's got a positive charge. So we go from a secondary carbocation to a tertiary carbocation. So the answer is yes, a carbocation rearrangement will happen here. What about in B? Would a carbocation rearrangement occur in B? Yay or nay? Okay, my students seem to be saying yes, that a carbocation rearrangement would occur. Look, I'm going to do the same exercise. If I highlight this carbon in blue and I highlight this carbon in yellow, if I was to shift one of the hydrogens from the carbon in blue, and let me show you what would happen. Let's draw both of them in. If you were to draw this hydride shift, you would end up with something that looks like this. And now you'd be left with one proton here and the positive charge. Well, this is a secondary carbocation, and so is this. So this is not going to happen. Okay, not going to happen. However, what if we were to shift this hydrogen, right? What if we were to shift that hydrogen over? Then we would end up with this, where we would have this carbon with 2 hydrogens on it now, and now we would have the positive charge here. This is a tertiary carbocation. And so, yes, we would get a carbocation rearrangement occurring here. Now, if there's somebody who's thinking, why wouldn't I get a methyl shift, right? Why is it a hydride shift and not a methyl shift? Because if you were to draw a methyl shift, I'll do it in green, you would end up with something that looks like this. You'd have the methyl group over here, okay? You'd have the one hydrogen here, and you'd have a positive charge there. You'd go from a secondary carbocation to a secondary carbocation. So you're not increasing the stability, and so it's the hydride shift that would occur in this case. All right, so let me delete that. Come on. There we go, and I'll delete this arrow. Okay, what about C? Would a carbocation rearrangement occur in C? What do my students say? No. The answer is no, would not happen. There's no hydride shift that could occur there to stabilize the molecule. Well, the last one is D. Let's take a quick look at it. You're starting it with a secondary carbocation. Would a carbocation, or would a carbocation rearrangement occur here? Who's got an idea? Yeah, my students are saying yes, one would occur. Well, you know that you've got two hydrogens here. If you were to shift this one over here, one of those over, you would still end up with a secondary carbocation, wouldn't you? Right? You'd end up with one hydrogen here, right? And then you've got a carbocation there. However, this is a more stable carbocation because this one is secondary allylic. So it is a more stable carbocation. All right, there we go. Well, with that in mind, let's turn our attention to some practice problems. And so I picked out questions 6.37 and 6.38. So I'd like you to start with those ones. I'm going to give you a few minutes to work on it. I'm just going to go upstairs and grab some water because I forgot to bring some down here. But again, it's question 6.37 and 6.38, and I'll be right back in a jiff. Could anybody tell me what's happening in the first step? Would this be a nucleophilic attack? So we have nucleophilic attack, proton transfer, loss of leaving group, and rearrangement. First step, so this step right here, going from here to here. What's going on here? Yeah, it's a nucleophilic attack, right? The hydroxide is acting as a nucleophile. Here you have the hydroxide by itself. You see that it manifested itself here somehow. And so it is acting as a nucleophile, right? We can draw in the lone pairs. If you want to draw the curved arrow starting on the negative charge, that's okay. I don't like to do it as your instructor. But you see that this is my nucleophile and that this carbon here is acting as my electrophile. So we have a pair of electrons. We start on the lone pair, and then we have a nucleophilic attack like this. You're like, there's something else that must have occurred here because this bond isn't here anymore. This is got a double bond. This is different, right? There's a whole bunch of differences because if you were to just draw this first arrow the way that I have it, there's a big problem there. Now that carbon has 5 bonds. And so we have to take this pair of electrons from the pi bond and move it over here to make a new pi bond. But then that would give this carbon 5 bonds. And so we're going to take this pair of electrons and move it between the carbon and the nitrogen like this to form this double bond, which would give the nitrogen too many bonds. And so we're going to have to break this pi bond and move it up here so that we end up with a negative charge on our oxygen. So a total of 4 curved arrows are required for this nucleophilic attack in our first step. What's happening in the second step? It must be a loss of leaving group, right? This is a loss of leaving group. The key is that you're losing something here, okay? And you can see there's going to be quite a few arrows drawn here. Now, you need to know that a nitro group, if you draw this molecule out, so this is para-nitrophenol is what it's called. The nitro is a nitrogen, okay? It's got a negative charge on one of the oxygens, like this. Okay, so this is the Lewis structure of a nitro group, and that's going to help you get from here to here, right? Because you see that this is not a nitro group. It's a nitro, but you've got extra electron density up here. And so if you're ever confused, you can start by maybe drawing the lone pairs in. Put in all the lone pairs because maybe you'll need them. We have some lone pairs here and here. There's here. These ones won't be important, but we can put them in there. So now we've got all the lone pairs drawn in. You see that we've reformed a pi bond here. We've reformed a pi bond here. We're going to lose this pi bond, right? And we're going to lose this pi bond. So let's start drawing some curved arrows. And of course, if we're reestablishing the nitro group, we're going to have to make a new pi bond here. So that's where we're going to start, right? In order for that leaving group to leave, we're going to start way at the bottom, and we're going to say, okay, we're going to form a new pi bond here. We're going to take this pair of electrons and form a new pi bond here, right? That's this one here. We're going to take this pair of electrons. We're going to form a new pi bond here. And then we're going to have the loss of our leaving. Oops, I'm losing the wrong leaving group, aren't I? We're going to lose this leaving group, right? If you have CH3 carbon with 2 double bonds to oxygen, and then you have this, okay, that's the same thing as CH3 SO3 minus, okay? It's just the Lewis structure drawn for you there. All right, so we have a loss of leaving group in the second step. And then what's going on in the last step? Could anybody tell me what's happening in the last step? Yeah, the last step is a proton transfer, right? The hydroxide is behaving as a base, right? And it's taking, I'm going to draw it to this one because you have to show the bond between the hydrogen and the oxygen. So we end up with our proton transfer in the last step. So I'll just cross this guy out and we'll use this one. And if you're like, why did you scribble that out, Mr. Dion? It's not that it's not important. It's just you have to show that bond. You can't do this kind of crap, okay? You can't draw a bond and do something that doesn't exist, okay? You've got to show proper curved arrows. So you got to redraw the molecule sometimes so that you can show the flow of electrons like that in our proton transfer. All right, let's take a look at the next one. Next one's a long one, but look what kind of cool stuff you can do in organic chemistry. You start it with this dialdehyde, and you treat it with acid, and then you end up with this funky molecule here. That's kind of cool. Okay, so that's something we might look at later. Well, let's just take a look at the very first step. So we're starting right here. Could anybody tell me what's happening in the first step? And it's not a trick question. Yeah, it's a proton transfer, right? You're starting it with this carbonyl that has no protons on it. It's got a proton here, so that's a clue that it's a proton transfer. You start with the tail of the arrow on the lone pair. You draw it over to the hydrogen like this. That's the bond that's being formed. That's this new bond right here. Then you're going to break a bond, right? You're going to break this bond right here, and you're going to put a lone pair down onto this oxygen. So now you're going to be left over with water, right? Here's that water molecule that was formed from here, right? You end up with water. So now we've got water in the next step, and we have our protonated carbonyl. Could anybody tell me what's happening in this step right here? Yeah, this is a nucleophilic attack, right? We have our water, which is behaving as a nucleophile, right? If you were to draw this curved arrow here, right, to draw the resonance structure, you'd see that that carbon is definitely electrophilic, right? It's strongly electrophilic. And so our nucleophile, and I'm just going to remove this curved arrow here, our nucleophile is going to attack the electrophilic carbon like this, okay? But that's not enough. If I was to just draw that curved arrow, then I'd have a carbon with 5 bonds. I can't have 5 bonds on a carbon, and so I have to break this pi bond and put the electrons up here like this, which gives us this molecule. So there's our nucleophilic attack. Maybe I should be more consistent with my colors here. There we go. So we're going to attack this electrophilic center, and we have a curved arrow here. So that's our nucleophilic attack. Next step, going from here to here. Could anybody tell me what's happening in the next step? Yeah, thanks, Kayla. It's another proton transfer, right? We're starting it with a proton here, and then it's gone here. So that means the water is going to take one of these protons. And if you're like, Mr. Dion, could I draw it? Could I draw it to that proton? Sure, be my guest, okay? Mr. Dion, can I draw the arrow from this lone pair? Sure, you can draw it however you want, okay? There you go. And you put the pair of electrons down here. So this is a proton transfer. And look what happens. When the water takes this proton, you end up with what? Hydronium in the next step. Have you noticed that when you look at this mechanism, it goes from hydronium to water to water to hydronium, right? It's just all in equilibrium. Okay, well, let's look at the next step. Let's zoom in on it. Okay, next step. I'll use my blue pen again. So what's happening in the next step? You're ending up starting with a carbonyl that's not protonated, and then it becomes protonated. So this must be a proton transfer. How is the proton being transferred, right? The carbonyl, lone pair on the oxygen, is taking this hydrogen. If you want to draw the arrow to another hydrogen in the hydronium, go for it. Draw it there, and then put a pair of electrons on the oxygen. So we end up with this protonated carbonyl. In this proton transfer, this next one is kind of tricky. Could anybody tell me what's going on in this next step? You go from this linear molecule to something that's cyclic. Not a loss of leaving group because we're not losing anything. It's not a rearrangement. It looks like a rearrangement, kind of, maybe, because you're going from something that's linear. Yeah, this is a nucleophilic attack. Remember, you got to follow the order of events, right? We start here, and we're going in this direction, okay? That's the steps you want to follow, okay? Start at the beginning and just follow it step by step to the very end, okay? So that means we're starting with this molecule and we're ending up, or this intermediate, we're ending up with this intermediate. So how did we get there? It's a nucleophilic attack, isn't it? Right? And if you're like, a nucleophilic attack, look, a pair of a lone pair is going to attack right here, and we do this. Look, count all the atoms in the ring that you would have. You'd have 1, 2, 3, 4, 5, 6. Look, you've got 1, 2, 3, 4, 5, 6, like that. So we form a 6-membered ring, and then in the very last step, it's another proton transfer. This is just a proton transfer where a water molecule takes the hydrogen, and this pair of electrons ends up on the oxygen, and there you go. There's your final product. There you go. And that's how you do these kinds of questions.